something we did last class is we started from the most elemental thing that was our differential energy balance. And we said, if we are in steady state and the properties are constant, we came to the conclusion that the difference in temperature, right, was proportional to the heat that was moving, right? We were using a wall, right? And I mentioned to you how this wall is an idealization because it's an infinitely tall, infinitely wide wall, right? And now this idealization is very useful. For example, something I didn't mention to you, but imagine you're calculating heat transfer on a big tank, right? Big tank, right? And the wall is relatively thin compared to the diameter, right? So your wall is not plane anymore, right? It's a cylinder now. Now the cool thing is, just like we think this table is flat, but we know it's not really flat, right? Because the Earth is round, right? In reality, everything that seems flat in reality is something round, but in this distance looks pretty flat to me. From the point of view of heat transfer, if the wall is thin enough, it's going to look pretty flat to the energy that is being transferred. So this idealization of a plane wall actually is pretty awesome, because you can do not only now cylinders and spheres too, as long as the thickness is thin, but you can also do crazy shapes, right? Who cares, as long as it is thin compared to the other dimensions, right? So very, very powerful. And we did this with a very trivial equation. So we came to this, and we said we're going to give a name to this proportionality constant. What was the name? R. Okay, R is the symbol. What would be the name? Yeah, right? This is a thermal resistance, right? So delta T equals R times Q. And now the next step, that was kind of the trivial thing to do, is, all right, I'm going to define R. And R is going to be delta T over Q. Let's talk about thermal resistance of plane wall. Right, and when we did this work that led us to see this proportionality, we saw that in a wall, right? And you know what I'm doing here, right? I'm making a cut of the wall as if I'm seeing it from the side, right? And we have TS1 here, TS2 here, right? And we had that the heat that moved through this wall. What is the heat transfer mechanism through the wall? Conduction, right? Can it be any other? Now, how about glass? If I have transparent glass, can I have radiation inside that glass? Okay, some say yes, some say no. By the way, everybody is right. Now, here's the catch. The fact that you see across through a window means some radiation got through, right? But that's the radiation in the wavelength of the visible wavelength, right? That visible wavelength is just shy of a micron, right? And that corresponds at 6,000 Kelvin. That is the temperature of the surface of the sun, right? Now, we seldom work with those temperatures. We work with 20 degrees, 100 degrees, 1,000 degrees, right? But 6,000 Kelvin, very uncommon. When you have those lower temperatures, you're going to see in the last week of class, the wavelength is much bigger. And this is a funny thing. The transparent glass is black to thermal radiation, right? So if I bring a thermal camera, and when we do radiation, I'll show you some photos, and I take a thermal image of you, not only you look funny all in colors according to how you are, but your glasses look dark, right? Water, same thing. So what we say in this class, and it's an approximation, but a pretty good one, is all solids are opaque from the point of view of thermal radiation. So you can get me the nicest glass, I'm going to say it's opaque. Of course, you can have this calcium fluoride, the special glasses that are transparent to radiation. I'm not going to worry about those exceptions. Liquids, like water. We're going to say is opaque to radiation. So yes, you can see through water, but the infrared radiation that it brings heat, no, that doesn't go through the water, right? Air, yes, we're going to say air is totally transparent, or argon or helium or whatever. Anyway, so through this wall we can only have conduction, right? Can I have convection inside the wall? You guys don't know all the mechanisms, the subtleties of convection, but I'm getting warmed up here. No, because convection is associated with fluids, right? Convection is associated with the heat that is transferred by a combination of conduction and advection in a fluid that is deforming, right? So essentially, if we take our class seriously, as you should, we discard 2 of the mechanisms and we have only one left, right? Q conduction. And what we saw is that the Q conduction in the wall was is this sign, did I put the right sign, is the sign correct? Did I miss a minus? What happened there? If I'm not writing differential equations or anything like that, I'm going to stop putting the sign, writing the sign, because I know it goes from hot to cold, right? I'll keep track of that. Our definition of resistance of conduction, thermal resistance of conduction, that is delta T over Q, tells us it's going to be L over Ka. This is very convenient, because the K is the material with which the wall is made. You would know. Actually, if you have the book, you would see all kind of thermal conductivities, K, right? For brick, for insulation, all kind of things. L, what is L? I didn't mark it here, but what is L in this wall? Thickness, right? Funny notation, but makes kind of sense, but it can throw you off. L is the thickness of the wall. So you would know that. And here you have the area of the wall. You would measure it and you would know. Now, there is an associated concept that has this horrible symbol that you can perfectly say thermal conductivity per unit area. That's okay. That is the inverse of resistivity, of resistance, or resistivity. But we seldom use that, and we use this R double prime. Most of the time, when we write double prime, means whatever it was per square meter, right? Except with the resistance, right? So please don't be thrown off by this. This is R times A, which is L over K. Right, and this is convenient when we have, like in a wall, the inside area and the outside area is the same. So I'm going to add it like here is subscript. I'm going to call it ref. For a wall or something like this piece of paper, the area this side is the same as the area on the other side. Big deal. But if I have a thick cylinder, the area inside the thick cylinder is smaller than the area outside the thick cylinder, right? Okay, when we start doing radial symmetry, you're going to see that that matters. So you have to commit to an area of reference. Are we making a reference to the inside diameter or the outside diameter? I want to hear suggestions about thermal resistance. Which one of you already anticipated this? Of convection. All right. Who can suggest how to get some sort of indication for thermal resistance of convection? All right, you say all the same. I agree. Let's go one step at a time. So what is Q convection? I like it. You said it right. So I'm going to call it delta T because the way you were saying it is if it is the hot wall is hotter, but might be colder. So delta T, resistance of convection, would be then delta T over Q, which is 1 over HA. Cool. And look at this. This resistance per unit area, which is not quite quality, this R double prime, is 1 over H. So I'm going to make a box in this guy here. I'm going to make a box on this other one here. Right? And H, does anybody remember the name of that symbol? Convection coefficient, right? So, good. And this is getting pretty interesting.